Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3, Section 3. So we would like to present exercise 1, simulating the power system response for the system stability analysis. So before we continue our presentation, I would like to introduce our team members. The first one is Ikmal Arif with metric number DE220190. The second is Hazwan Azraf with the metric number AE to 10025, and last but not least is me, which is Muhammad Izhan with the metric number DE220147. Okay, now we continue for the introduction of this exercise. So exercise 1, the objective is to simulate the effects of a permanent bolted 3-phase fault at the bus 8 in a 2-area power system. And this purpose is to evaluate the rotor angle stability for each generator under severe fault conditions. The simulation tools that we use is MATLAB Simulink to model the system and implement the fault scenario. And based on the observation, we can analyze the rotor angles, rotor speed, and the electrical power output during the disturbance. The learning outcome that we can get from this lab is to gain the insight into the system dynamic response and improve our ability to analyze and maintain the power system stability in a real world application. So the objective of this lab, the first one is to model a test system model of the power system using the MATLAB Simulink. The second is to analyze the dynamic response of the system following a disturbance. And the third, which is to work in a group to solve the complex power system problems in a group within a limited amount of time. So we will continue for the methodology. So the first one, we will identify the objective and scope of the experiment of this lab, and then we will continue the some research about the power system stability. After that, we continue with design a 2-area power system model in the MATLAB Simulink model, and we continue with the set the parameter for each block, where the parameter is defined in the lab sheet. After that, we will continue add the disturbance to the systems, and we will continue to analyze the simulation based on the graph of rotor angle, rotor speed, and the power electrical. After that, we will see is it fulfill the requirements. If no, we will continue to add the disturbance to the system. If yes, we will record the result, analysis, and do discussion and also documentation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hazwan Azraf bin Muhammad Azman. My metric number is AE210025. Now we move to the slide of the stable versus the unstable power system. For the stable power system, the definition is for the stable power system, a power system is stable if it can return to a steady operating condition after a disturbance. So the behavior for the stable power system is generators remain in the synchronizations, rotor angles settle over time, and also the effect is it is continuous, reliable for the power delivery. For the unstable power system, the definition is a power system is unstable if it fails to return to a steady state after a disturbance. So the behavior for the unstable power system is generate losses for the synchronizations, and the rotor angles continue to diverge synchronizations, and also for the rotor angles settle over time. So the effects of the unstable power system is risk of blackouts, equipment damage, and also the operational failure. That's all for this slide. Thank you. For this slide, our experimental procedures for this group, Group 3, Section 3, which is we need to conduct and detect the data at bus 8, which is our fault is at the bus 8. And also our load is we label as area 1 and also area 2. You can see at the screen at the left and also the right with the turquoise color. And also for the circuit breaker 1 and also circuit breaker 2, we label as BRK1 and also BRK2. This is the results and discussions for the stable condition without fault, where the stable plot without fault and circuit breaker use. So this is the image. If there is no fault and circuit breaker use, which we can see that is the stable graph that obtained from the MATLAB simulations. Also, this is a stable condition without fault for the machine plot without fault and circuit breaker use. So we obtain the graph from the MATLAB simulation for all the colors, which for the yellow colors, blue color, red color, and also for the green color. This is the result and discussion for unstable condition with fault. So from the image, we can see that the graph and the fault obtained occurs at the t is equal to 5 seconds, and at time 8.118 seconds, the machine lost the synchronization for the machine plot with fault and without circuit breaker use. For this slide, this is the another unstable condition with fault, which is for the machine plot with fault and without circuit breaker use. So it is the same with the previous slide, which is at t is equal to 5 seconds, the fault occurs, and at t is equal to 8.118 seconds, the simulation machines lost the synchronizations. So we can analyze from this data that each graph give different shape of the data obtained.
Assalamualaikum. Hi, my name is Muhammad Iqbal Arif bin Hadi. So I'm going to present about our unstable condition plot. For the for this plot is unstable condition with fault and circuit breaker opening at 5.81 second. So we can see here the fault occur at 5 second and the circuit breaker opening at 5.81 second. So the system can stabilize itself and the simulation stop at about 10 seconds. So this is the um, machine plot for the unstable system with the circuit breaker opening at 5.81 second. So this is the circuit breaker takes 0.81 second to open, and the system are unable to stabilize itself after the circuit breaker disconnect the load from the fault. So this is our stable condition of the system with the circuit breaker opening at 5.8 second, which is 0.8 second clearance time. So we can see here the fault occur at 5 second and the circuit breaker opening at 5.8, and the system are able to stabilize itself after the circuit breaker opening. So this is the plot of the machine. So it also stable with the circuit breaker opening at 5.8 second. The clearance time is 0.8 second. So we conclude the CCT. The critical clearance time is 0.8 second. And CCA for yellow is 76.48 degree. Blue is 58.54 degree and red is 16.47 degree. So now I'm going to present our MATLAB simulation. So this is our MATLAB model. So here we have the fault at bus 8 here. Um, so the fault will occur at 5 seconds, and this is breaker 1 and breaker 2. So firstly I will show the unstable version of the simulation. So from our trial we have 5.81 switching time of the circuit breaker. So now I will run the simulation. So here we can see the here at 5 seconds the fault occur, and the switching occur here at 5.81 second. So the simulation is done, and we can see the simulation finish at 10.013 second. So this show the unstable condition of the simulation. So this is the system plot, and here is the machine plot for the unstable version. So this is 5.81 switching time. So it takes 0.81 second for the circuit breaker to open. So now I will show the stable version of the simulation. With this from our trial, we get 5.80. So I will run the simulation again. For a stable condition. So we can see the fault occur here at 5 seconds. And the circuit breaker open at 5.8 seconds. So it takes 0.8 seconds for the circuit breaker to open from the fault. So after the simulation finish, you can see the simulation. The system are able to stabilize itself after the circuit breaker open. So this is the machine fault. We can see also the stable condition of the plot. So what we can conclude here is our CCT, which is critical clearance time, is 0.8 second, and for the CCA, critical clearance angle, for the yellow we have 76.48 degree. For the blue we have 58.54 degree, and also for the red 16.47 degree. So as conclusion, we had gained deep understanding of power system response and stability analysis concept by creating and simulating the power system model using MATLAB Simulink, and we had analyzed the system response to disturbance and assess its stability. And by doing this, we have improved our ability to collaborate effectively on complex power system issue. We have demonstrated the simulation method support um, effective handling of real-world power system problems. Um, we also enhance our skill and familiarity of using simulation tool, especially MATLAB Simulink, uh, related to power system stability, and we um, able to identify critical metrics such as CCT and CCA of the power system. And finally, we have strengthened our understanding of the transient stability and the importance of accurate modeling and timely protection mechanism in modern power system. So that's all from us. Thank you.